Let's do problem 9 and 10 in this snippet. In problem 9, this is actually a three-dimensional FBD. I've got vertical forces and then I've got forces in a horizontal plane. And in a problem like this, or any of our problems, I hope that you will feel comfortable at a certain point in just saying, okay, if I didn't have somebody ask me to drive this part and then drive that part and then combine them to get this part, that you could just say, if somebody said, hey, what's the tension here? You could go step by step. Start out, in this particular case with a string around it, let's look at a little piece of it and look at balancing forces on that piece. Well, the little piece, I'll take a delta m corresponding to some delta theta. So actually the delta m will be the total mass times this fraction, delta theta over 2 pi, subtended by delta theta. Now, vertically, things not sliding down. Without friction, this thing is just sliding down. I've got some friction up, balancing the weight down. It's all incremental, just delta m and some delta friction. Horizontally, I got a normal force pushing out, it's not crushing and pulling in on the cylinder, balanced by the components of the tension that are along this radial direction. By the way, so this is a tiny little angle that we're going to look at for a tiny little piece here. So these are huge tensions compared with, the normal forces over Earth, but it's a tiny little component of them measured by delta theta. Well, you'll see that in a second. What I've got here is this little piece. What are the forces on it? Well, that normal force. And then tangential to the circle is the tension pulling on that side and the tension pulling on that side. And I do a golden triangle for each. I want to know, ultimately, a component parallel to this radial direction. So that's one of my legs, and that tells me the other leg's perpendicular to it. And if this whole angle is delta theta, then you can see that this is half of it because this horizontal line is perpendicular to that vertical line in the center. And this, of course, is perpendicular to that radial line. And so it's this half angle that is similar triangles with this triangle. And it's that half angle that comes in here, delta theta over 2. Okay, I got a right triangle, got my components, sines and cosines. The cosine guys just cancel each other horizontally. The vertical guys add up to cancel delta n. And I'm considering smaller and smaller in this limit, and I take then the sine of delta theta over 2, and that limit goes to just delta theta over 2. The ratio of this is equal to 1 as delta theta gets smaller and smaller. So I need to do that in order to finally treat this as a point. Well, now I got a relationship between delta n and t. I got a relationship between friction and weight, but the friction can only be so big. So the tension can only be so small because the tension has got to supply this normal force. I get that mu st, I just substitute this in this side and this in that side, and I get mu st delta theta is greater than or equal to mg delta theta over 2 pi, and the delta thetas cancel out. Again, I look at smaller and smaller delta theta so that I am talking about a single point here and here in the limit. In this case, I had to have friction. If you had like a cone and had a rope hung around it, you would have a normal force that would give a component vertically, and you wouldn't need friction. and you could handle that kind of problem. Again, if you were given that problem and you weren't laid out to say, do this, 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 and this, you could start building up the story. By now you've got the experience. Problem 10. Speaking of a banked, a wall here, we've got a banked road. We've got normal force, friction force, weight, golden triangles all over the place. If this is theta, then that's theta, and then that has to be theta because they're both complementary to that. And now I've got, why did I choose these triangles? Because these legs, I needed vertical and horizontal to be able to home right in on the centripetal acceleration horizontally inward toward the center of the circle that this road represents, and vertical where there's no acceleration. You're getting familiar with that with some other problems we've done before. And if I were doing horizontal, F equals ma, I've got centripetal acceleration inward provided by the components from my triangles, from the normal and the force of friction. You get the signs on all of these guys by recognizing, remember that it's that plus that adding up to this, and so you know the directions of the components besides their magnitudes. And this problem is a familiar, something that makes complete sense to you. If I had huge friction, I wouldn't have to worry about slipping down the road, slipping down the bank. So V, the minimum V that I would need could go smaller and smaller and smaller, still not slide down. So if I put in the maximum friction I got, then I could get sort of the minimum speed that I could go before sliding down. In fact, if the angle were small enough, it wouldn't slide down at all with my friction. But in general, it's the possibility is there.